normally do this like this. This is like a pistol, and you shoot directly on the surface of the equipment, on the thing around the display, maybe on some touch buttons. And the equipment is allowed to maybe flicker a little bit, that's okay on the display, but it should not come out of control somehow. So we have different levels of ESD testing, but it's just good to know. This is just, we try to disturb the equipment, and it should withstand this. Normally it's a matter of a good ground in the equipment. You should have a good ground inside, especially around displays and whatever. That helps a lot. Then we do burst. Burst is something that happens when you, for instance, you switch some inductive load or whatever. It can happen that you have a burst. These are really fast transients. Really fast, which means for us, fast transients, which with a fast rising time, for me, is high frequency. So these bursts, you see, these are a packet, a duration that we do here. They will disturb the equipment, but it's not so, you see, it's not so very high energy, so it's something you can handle. It's not so bad. But you see, it's 5 kilohertz, and it has to be done regularly. It's a procedure that you do this regularly. This burst packets like this is 15 milliseconds, then you wait 300 milliseconds, do it again, and see what happens. And lightning, this is the surge. It's a simulated lightning. It's when the flash happens to your house or whatever. It may happen that you have a surge, a pulse on the mains network. It's a high energy pulse. This is high energy. And it really can blow up things if it's not proper made. So this is the pulse. It has a rise time of 1.2 microseconds and 50 microseconds time. But this is a high energy pulse. Under normal conditions, we have 2,000 amps going through here. So it's the power. You may use some varistors or whatever to control this. Here we go. So these are the main immunity tests. Look. Here we see an example. This is how it could look like when you do a measurement. It could be something like this. Here you see the limit of the standard, and you should be below the limit. Now, when you have something like this, and here you have several peaks above the limit, you may have to look for a filter or whatever to control this, to bring this below, because usually it's not, especially when the design is finished, it's not easy to do something else. So it's the easiest way is to have a filter. And of course, filter usually works very broad. So it will work for broad, for a wide frequency range, and it will bring down the whole noise underneath this limit. This is the best way when it works like that. When you do an EMC measurement, first it looks like that, and with the filters like that, everything is fine, probably everybody's happy. But it's not all the time like that. important. We have two ways of noise that we talking about. We talk about symmetrical and asymmetrical. What does this mean? We to say it very simple, symmetrical is line to neutral or line to line. Noise, a voltage, that is coming from one line, like line to neutral, that's symmetrical. This is the test setup. According standard, we use this transformers here. But what we do is really we measure line to line, these are the lines, and this is ground here. Asymmetrical is line and neutral to ground. So at the beginning you often don't know which effect we working with. And I cannot tell you in general what effect it is, but with different setups you can find it out. Filter usually works for both effects. Any kind of a standard filter is made to have a good attenuation for asymmetrical and symmetrical. So you should not care too much about this. It's only for special applications, special noise where you might have to know what it is. In general, at the beginning, when you do the first measurement, it's not so important. But it's important to understand it. This is something else we're dealing with. It's also this, we'll come to this later on. We have a leakage current, a current that goes to ground. Every capacitor connected to the ground or to the chassis may cause a current to ground, constantly current, and if the ground is disconnected somehow to a fault, an error, whatever, and you touch it, it might hurt you. So this is really something dangerous, something that we should be aware of in our filter. Also here, when it's well made, it shouldn't be a problem. You should be able to touch this. I will come to this topic later on because leakage current is very important for most of the application. Not so much for industrial, but for most of the application, you should be aware of the leakage current. Why should you be aware of the linkage current? Because we have so many regulations here. Different standards require different limits of leakage current. And the problem is, if the leakage current is just too high, you might have a fault current detector in the house, in the building, and this might drop off, and just because of the leakage current. And be aware, most of the filters, if it's not a medical type filter, they produce a leakage current. And this is not the only one in the application. Normally, you have different sources of leakage current, not just the filter. Especially inverters produce leakage current. Or any kind of frequency controlled unit. That's because of the wiper. Yes. Because the Y-cap is a very good attenuator. We like it really very much, but we don't like the leakage currents. So we have to find a balance in between. But you're right, it's because of the Y-cap. I will come to this later when we have a look on all the elements of the filters. So it's, you know, the perfect filter would just be with a very big Y-cap, but we are not allowed to use it, of course. because of these leakage current regulations. So you have to be aware of, usually we use just 2.2 nanofarad. This is nothing. This is a very small capacity. But this guarantees us that the leakage current is below 0.5 milliamps. It's also very low.